Wabarakatuh, and good afternoon, everyone.
Good afternoon, Doctor.
I hope all of you are uh, locking down yourself in your home and not um, moving around unnecessarily. Okay. Uh, yeah. So all the best to us for the next 2 weeks. This lockdown, oh my god. Yeah, but I believe for most of us it doesn't change much because we have been attending classes, online classes for uh, um, almost 1.5 years or so. PKP lockdown, so doesn't really make much difference now, right? Uh, all right. It's just that I'm not so sure if any of you sort of like have to attend the classes at other places, like let's say, maybe some of you may need to go outside to get a better internet connection. So for those of you who cannot attend classes due to that, like in a sense that you cannot go out to go to cyber cafes, or I don't know, maybe other places that have better connection, please let me know. um, um, if you know a friend, please let them know to let me know that they are having this problem. Okay, and then maybe we can sort out alternative ways of you either like for the lectures as well as the viva later. Okay, all right. Yeah. So I think I better start the recording first. All right. Okay, so today we're going to be looking at graph algorithm part 2. I just noticed there's a typo in the front page. Okay, so we're going to be looking at graph algorithm part 2. Last week, we looked at some graph algorithm, and we have looked at what did we do last week? So uh, so basically, last week, what we do is we do the BFS, the FS, and then we have the topological sort as well as the MST, right? The minimal spanning tree, where we looked at Kruskal and Prim's algorithm. Okay, so today we're going to be looking at several. I think we're going to be looking at three more graph algorithm. Last week, for the BFS, the FS, and topological sort, we don't really do any not really. It's not like we don't do any optimization, but basically, the edge, there's no weight, right? We are not calculating any weight. All we have to do is that for BFS, DFS, we want to do some search, and then topological sort, we want to have some order, and then we look at MST, we started looking at the weighted edges, okay, whereby we want to find what is the minimum cost of spanning tree that you can get out of a graph. Okay, and then for MST, last week we applied the greedy approach, okay, for the algorithm to find the minimum spanning tree. Okay, so today we're going to be looking at part 2. We're going to be looking at graph algorithm, which we call the single source shortest path. So we're going to be looking at Bellman's Ford and Dijkstra algorithm. And then we're going to be looking at Floyd-Warshall, okay, which is for all pair shortest path. We're not going to be looking at Johnson algorithm. I decided to take out Johnson algorithm. For those of you who are interested, you can read it as your additional information. Okay. All right. So for as like what we did last week, whereby we used the greedy approach to for the MST and for the shortest for the BFS and DFS. For today's lecture, we're going to see that this algorithm will be some of these algorithm will be using greedy, and one of it you can solve it using greedy as well as dynamic programming approach. Okay, so we're going to be looking at dynamic programming next week, but basically we're going to be looking at one algorithm that actually applies, okay, the dynamic programming approach in its algorithm. All right. So let's start with the first one, which is the shortest path problem. Okay, so basically, when you talk about the shortest path, is when you want, it is an optimization problem whereby usually you can solve this using greedy or dynamic programming approach. Okay, and then so usually the input for this would be a graph with weights or costs, either usually it is associated with the edge. Okay, with and then the output is usually, because we want to find the shortest path, it would be a list of edges forming the shortest path. Okay, either from one node to another. Okay, so as you can see here, either the shortest path between um, two vertices. Okay, sorry. So either you want to find the shortest path between two vertices. Okay, shortest path from one node to all other vertices, or you want to find the shortest path between all pairs of vertices. Okay, so these are the things that you can do when you want to find the shortest path problem, all right, in a graph. So so basically what we're going to do is we're going to calculate the actual distances between these two nodes based on the weight or the cost of all the edges for the vertices here. And for last week, we do not, for the MST, all the edge are positive, right? Because we want to, we assume that all the edges are positive. But today we're going to be seeing some negative edges as well. Okay, you're going to, this algorithm will consider negative edges as well. Some may not be appropriate because it's probably it's not going to give you the most optimum answer, but all these algorithms that we're going to be seeing today can handle negative edges. Okay, so just some notes when you talk about negative edges. So we assume that like, since we can apply graph on things like I don't know, maybe I don't know, maybe like a set of movements or schedule, like somehow there would be a reduced a discounts, let's say, for example, in terms of the process. So that's why some of the graph will may include negative edges. Okay, so did I switch off light? Okay. All right. So basically, it would be so some of the, so you may find that some graph will have that negative value, okay, for the edges. All right. So before we go forward with the algorithm, like the Dijkstra, Bellman, and Floyd Warshall, let's look at this concept called the relaxation. So all these algorithms will apply this relaxation process, okay, whereby if, like, let's say, for example, uh, um, so basically a relaxation, the purpose for that is you want to maintain the shortest path estimate between the two vertices, okay? So basically, we want to find what is the upper bound on the weight, okay, of the shortest path sources from S to V. And then the process of relaxing an edge of, like, let's say, for example, you have U and V, okay, with an edge, is testing whether you can improve the shortest path to found so far by going through U, and if so, we update the value of the distance. Okay, so let's say for example, maybe I will give you an example. Let's say for example, the most basic relaxation that concept that we are going to do is that, let's say for example, we have this node, okay, B and C. All right, so let's say for example, the distance of this is 5, the distance of this is 3. Okay, and then we want to start to find out what is the distance of B and C starting from A. Okay, so we say that at the moment A would be, the distance would be 0. So in order for us to know what is the distance for B, it would be, sorry, maybe I should put it this one so it will be much clearer. Okay, for us to know what is the distance from A to B, so we know that the distance from A to B would be 5, right? But the distance from, if like, let's say we want to find out what is the distance from A to C, at the moment we have no idea. So therefore, we say that the distance would be infinity, right? So when we want to do relaxation, so in a sense, when we want to find what is the distance from A to C, we sort of like uh, uh, try to relax the edge, right? By finding what is the shortest path through some nodes. Okay, so in this case, how we do relaxation is that in order for us to get to C, we know that until B, the distance that you have is 5, right? And then to get to C, you can go through B. Okay, so therefore we know, so we can update the distance instead of infinity from A to B is 5, and then in order to get to C, we add 3 into the edge. So therefore, instead of infinity, now we know that the distance here would be 8. Okay, so this process of finding what is the shortest path, okay, from one node to another node by going through some intermediate nodes, okay, is called the relaxation. So we can consider this. So if we look at the how do you call that, this formula, okay. So this is we consider this is U, this is V, okay. So basically, if you want to find out, if you want to relax the edge, so VD, okay, so we want to check if the distance of V is bigger than the distance of U plus the weight of the edge of U, the edge UV, okay. In this case, the distance, so maybe we stick to the original one yet first, okay, from A. So basically, the distance of V is infinity, the distance of U is 5, and the weight is 3. Okay, so if we add this, therefore, this one is actually bigger than 8, right? So we are going to say that, sorry. So we're going to say that the distance on, so this is actually this one. So therefore, we can say that the distance of V is actually U, distance of D plus weight of UV. All right, which is in this case would be 8. Okay, so that is how we do the relaxation. So now we know that the distance of our V is 8. Right? Okay, so that is the concept of relaxation. Okay, so with that in mind, let's look at Dijkstra. I don't know. Some people call it Dijkstra algorithm. Some calls it Dijkstra. So normally I call it Dijkstra algorithm. So yeah, but yeah.
Excuse
So
me, doctor.
yes,
Sorry, but are you supposed to be sharing your screen?
I am.
Because I don't know if it's
I
just me, but we
think it's
can
just
see
you.
your video.
Oh, how come I'm not sharing?
Oh,
Can you see my screen, class?
right now it's showing Dijkstra's algorithm.
Ah, yes. So you didn't see my screen this one now?
Yeah, like, because for me, it's just a video for some reason.
How about the rest?
You did
I
the
can see.
ABC and then 053 UV, that one, right? The
No, I
top
mean,
right. Is that the one you did, or is that? Uh,
I have been sharing my screen right from the beginning, because yeah. How about the rest? Have you can see the screen, right?
Okay, I'll
Yeah.
try and restart.
Yes.
Okay, so all right. So I think because sometimes the I don't know, I never been on the other side. So for me, because I have two screens, I know my iPad, so I know my screen is showing because my this one can see the one is displaying on the iPad. So that's why I proceed with that one just now. Okay. All right. So all of you are okay with relaxation, right? So because we're going to be using relaxation in uh, actually the concept is going to be applied in all the three algorithms that we're going to see today, right? Okay, so we're going to be looking at our first algorithm today called the Dijkstra algorithm. So this is a very fundamental algorithm for finding the shortest path. Okay, so it's a very simple, it's a very fundamental algorithm, and there's a lot of variation out of this in terms of the optimization. Okay, finding a better approach for finding the shortest path. But Dijkstra is one of the most fundamental shortest path algorithm that you can apply if you want to find the shortest path between one edge to one node to another. Okay, or between two vertices. All right. Okay. So for Dijkstra algorithm, it is used to solve a single source shortest path problem on a directed graph. So let's say, for example, you want to find what is the distance from A to any other vertices. Okay, so that is how why you want to apply the Dijkstra algorithm. Okay, so let's say, for example, we have okay, maybe we will just straight away go to the example, right? So for Dijkstra, it is solving the distance from, like, let's say, for example, we say that this as our starting point. So by applying the Dijkstra algorithm, we're going to be we are going to get what is the shortest distance from S into T, X, Y, and Z. Okay. All right. So here we are going to straight away apply the Dijkstra algorithm onto this example. So basically, what we're going to do is we're going to be repeatedly relaxing the edges. Okay. And hopefully, so in a sense, if you notice for Dijkstra, it is somehow using a greedy algorithm as well, because we are the way we relax our edges is by looking at what is the smallest value. We choose by choosing the smallest distance next. Okay. All right. So let's start. Let's say, for example, we say that our starting node is S. So what we're going to do here, as you can see, as there are two, these are directed graph. Okay, so you see that they are all, they have a directional edges. Okay, so for uh, uh, so this is the issue. Oh, what is this? I'm so sorry. One second. All right. I'm so sorry. I thought that one is supposed to be do not disturb. I don't know why they are still I think because it comes in from my laptop. But anyway, I'm so sorry. Okay. All right. So where were we? Okay. So basically, this is the initial state of our graph. Okay. So if you remember, so this would be the initial state. So we know that the distance from S would be 0, and the rest, since it is unknown, okay, the distance from S to T, the distance from S to X, distance from S to Y and Z, and so on and so forth, is unknown. So therefore, we say it is infinity. All right, infinity distance. Okay, so we're going to apply the Dijkstra algorithm, and we're going to find out what is the distance from S to each of these nodes. Okay, so let's start by doing the relaxation. So how do you choose the edge to relax? Is that first, since we start from S, we look here is S can go to T and S can go to Y. Okay, so between two of these edges, okay, 10 and 5, we are going to choose the smallest edge to relax. Okay, so in this case, we are going to choose this edge to relax, right? So therefore, we can update the distance from S to Y is 5. Oh, sorry, before that, before we do the relaxation, okay, so we're going to see that since that from S can go to T and S can go to Y, we can actually update the distance for T and Y from S, right? So in this case, S, the distance from S to T, this one would be 10, and from S to Y, this one would be 5, right? Okay, so out of this, all of these vertex, okay, or these nodes, I like to use the word nodes, okay, so maybe I will just stick to nodes. So out of all these nodes, 10, 5, infinity, and infinity, we are going to choose the smallest one to process next, okay? So in this case, the smallest one would be 5, so we are going to process node Y next. Okay, so from y can go, so we can see that the edges that coming out from 5 would be going to T, going to X, and going to Z, right? So therefore, we can update the distances of these connected nodes. Okay, so 5 going to T, so we can see, so let's try and see, so let's try to do the relaxation by looking at when we add 5 with 3 is 8. So therefore here we can relax it. We can do the update okay, the distance of 8. So y to x, so since this is 5 and y to x is 9 and this is infinity, so we can relax this edge and update this. This would become 14, right? 5 plus 9 is 14. And then the other one is y and z. So z, currently the distance from S to Z will be infinity, and you can reach Z through Y. Okay, we can reach Z through Y, okay, with the distance of 5 plus 2. So we can update instead of infinity. Now we can reach Z with the distance of 7. Okay, so that is done. That is fine. Did we miss any edge out of Y? No, right? Okay, so we're gonna do the same thing again by choosing which nodes to process next. Okay, so in this sense, in this case, we have to choose between 8, 14, and 7. So the smallest would be Z, right? So we're going to process Z next. So from Z, we know that Z can go to X and Z can go back to S. Okay, so basically we don't really consider one going back to the initial position. So we're going to see this edge. Okay, so now let's see if we can relax this edge. Okay, so 7 plus 6, we're going to get 13, which is smaller. So therefore, we can update the distance, for the distance for x to 13, because we know that you can reach x by going through z with the distance of 13. Okay, so we update that, and then that's fine. Okay, same goes again. We're going to consider which nodes to process. So we have 8 and 13. So we're going to choose node T. Okay, so we're going to process this node, and T can go to Y. T can also go to X, right? So since Y has been processed, we're not going to be relaxing that edge. We're going to be relaxing this edge. So 8 plus 1 is 9. So therefore, we know that X can actually be reached with the distance of 9 by going through node T. Okay, so therefore, we update this, and we update it into 9. And then therefore, and then we're going to be looking at what are the available, what are the nodes that haven't been processed. So this is the only one. And therefore, we have completed our algorithm. Okay, so now we can say that uh, so for T we have, sorry, so for T we have 8, we have 9, 7 and 5. These are the distance that you can reach from S. So let's say, for example, S can go to T with the distance of 8. Okay, so basically by going through Y, S to Y, Y to T, and then the distance would be 8, and so on and so forth. So this is how you apply the Dijkstra algorithm. Okay, so 8, 9, 7, 5. Okay, do you have any question about applying the Dijkstra algorithm to find the shortest path between one source to the rest of the nodes? Class, any question? Yes, no? You good?
I think okay, jap. 7. Yeah, okay.
Okay, so basically how you choose, so let me recap. What you do is that first you update what are the, so the edition state, we just update for S, and we update 10 and 5. So whatever edges not update lah, but we relax the edge, okay, by finding what is the shortest distance at that time. Okay, so when we start S, so we know that the distance of this is 0. So 0 plus 10, and we know that the distance from S to T at that time would be 10. Okay, and then the distance from S to Y initially would be 5. So how are you going to choose which nodes to process next? Is by looking at which nodes are having the smallest distance. Okay, to reach from S, and then you do the relaxation again. Okay, so that, yes.
Just to make sure, I think I don't know. I feel like I might have been confused a bit. But so relax in this case means like we let go of one of the possible paths and choose the preferable path, or what does relax mean in this case?
Relaxation is just you are trying to update what is the shortest path that you can go to that node through the previous node. The U, if you remember when I mentioned about the definition of U and V with this edge. So basically, when you do relaxation, okay, when you update the distance of this, basically what you're saying, what you're trying to say, that the update is that you can get to that distance, let's say distance X, through this node. So you have no idea from where this would be, but you know that in order for you to get through U to V with the value, the smallest value X is through this node, node U. Okay, and the shortest distance, like let's say this is the shortest distance of Y from you, you're probably going to have another different node from T. So therefore, basically, you keep track of from where that the shortest path came in from. So therefore, you can determine where how you can reach there with the shortest distance. Is that right? Basically, that is what we do. Maybe you can try and practice applying the shortest distance, and then you will understand how the relaxation occurs. Okay, it's just like
Okay.
you are relaxing the edge by, you know, like basically at that time, that point of time when you do the relaxation, that is the shortest path that you can reach that node through the previous node, the adjacent node that you come from. Okay, so
Okay, noted.
basically that is what you do, the concept of relaxation. All right, so the extra algorithm. Okay, so you can also uh, do this structure algorithm by updating the distance using table. Okay, so how should I do this? Okay, maybe I'll just open this in window so that it would be easier for you to see. Right? Can you see? Hopefully you can see it. I think the boxes are not, but never mind, the boxes is only for me to what. Okay, so you can actually calculate the distance by doing a distance, by keeping track of a distance table. Okay, like let's say for example, in this case we have node sorry, we have node, this is I need a blue. Okay, so we have node uh, S, T, X, Y, and Z, right? So these are the nodes that we have. Okay, what we're going to do is that we're going to update this table instead of we update the graph. Okay, so hopefully that's good enough. Okay, so the initial state, so we know that the initial state is with the initial, we coming, we will be looking from S. So here we can say that the distance would be 0, and the distance from S to the rest of the node would be infinity, right? Okay, and then we're going to choose S. Okay, we're going to choose S, and we're going to see S can go to, so in this case S can go to T, S can go to Y with 10 and 5. So we can update. So we can update this. So maybe we can just write this one as 0. So we can update the distance from S to T as 10, and the distance from S to Y as 5, and the rest would be infinity, right? Since we already choose this, we're gonna just to keep track that we have chosen select, we have processed that node, okay, which is node S. Now we are going to look at this list, okay, this list, and try to see which one is the have the smallest distance. So at the moment we see that Y have the smallest distance, so therefore we're going to process Y. Okay, so we're going to process Y, and then we're going to look at Y. Y can go to T with the value of 3. Okay, so since we know that this one we can Y with 5 can go to T with the distance 3, and then we try to add 5 plus 3 is 8. And then you see Y to T currently is actually 10, right? Here in the table, everything better. So we see okay. Okay, so basically we start, we choose Y, okay, to process, and we look at Y, and Y can actually go to T, and Y can actually go to X, and Y can go to Z. So we're going to see that here, so Y going to T, currently the distance is 10. So if we see here, Y can go to T uh, with this edge, and if we plus 5 plus 3 is actually lesser, so which is 8. So we can update our table. Instead of 10, we can say now it is 8. All right, and then Y to X. So since we have this one, we have 5, and then 5 plus 9 is 13. So Y to X at the moment is infinity. So we can update this table to 14. And then Y to Z, currently Y to Z is actually infinity. And if you look here, there's another edge at 5 plus 2 is actually 7. We can actually update this table into 7. And the rest we just copy it back. And then we want to make sure that we keep track of the processed nodes. So we circle it. And now we reach into this space, okay? And then again, we look here, we choose which one is the shortest distance. So in this case, the next one that we're going to process is we're going to process Z, okay? So we're going to process Z. We're going to see that Z can either going to S or going to X. So currently Z to X is 14. And we see that here, if we use the ZX edge here, which is 6, 7 plus 6, it is actually lesser, which is 13. So we can update our table into 13, right? And then Z cannot reach to T, so therefore the rest would still be the same, okay? 5, 7. So again, keep track of the process node. And again, we're going to choose which one is the next one to process by looking at the smallest at this time. So we're going to process T. Okay, we're going to process T, and we look at T. T can go to X. Only can go to X because the rest of the graph has been processed, because T can also, here if you can see that T can also go to Y, but Y has been processed. So currently the distance from T going to X is 13, right? And from here, we can say that the distance that you have here, which is 8, okay, you can actually get 2x through this edge, 8 plus 1, which is 9. So therefore, we found a shorter distance from T to X. So therefore, we can update here, become 9. All right. And then the rest, we can just copy it back in the value 0, 8, 5, 7. And again, we keep track of the process node. Again, since this one is the last one, so therefore we're going to process X. And since X is the last one, and then therefore this would be the shortest distance from S to the rest of the node. Okay, so from S to X, S to T would be 8. S to sorry, I think it would be easier. From S, okay, from S to from S to T would be 8. From S to Z would be 7. S to Y would be 5. Okay, so you can also use the table to update the distance for your graph. Okay, so actually when you do your implementation, basically this is the thing that you can implement to keep track of the changes of the edge relaxation, okay, for each of the nodes. Okay, any question, class, for this one? Should be okay, right?
Okay.
Try you try it, and then we will see. I think we have how do you call that? I don't know whether we have a question for this one. I haven't looked at the topic, but I had a feeling that I remember we have a question for this. But try it on your own. Okay. This the example here, and then if you have any question, then we can discuss during the tutorial later. Okay. All right. So I probably need going to use this one later. So I'm just gonna go back. Okay. So for the next algorithm, we're going to be looking at Bellman-Ford. Okay. So before that, the running time complexity for Dijkstra algorithm is V squared. Okay, because if you see here, what we are doing is we are relaxing. So for each node, we sort of like relaxing up. At the moment, there's a possibility that each of these node is connected to the rest of the node. Therefore, that's why the worst case running time complexity for Dijkstra is order of V squared. Okay, the number of vertices squared. Okay. So because we assume that there's a possibility that you're gonna have all nodes connected to each other. So this one connected to this, connected to this. So the possibility of did I miss anything? Yeah. So basically, in this case, the running time complexity for running the Dijkstra can go up into order of V squared. Okay. All right. Okay, so that is for the Dijkstra. Now we're going to be looking at Bellman-Ford. Okay, before we go into Bellman-Ford, in our example here, we don't really have negative edge. Okay, so all of our edges are positive. So what if there's a negative edge in the graph? You can still use Dijkstra. It's just that it is not going to give you a complete. Not saying that it's not going to give you a complete distance, but you may miss an edge. Okay, that actually may give you a smaller distance because of the negative edge. Okay. You can still apply the Dijkstra. It's just that it's sometimes you may not get the really shortest distance because due to maybe during tutorial I'll give you an example of that. But yeah, you can still use negative edges with the Dijkstra, but the possibility of you not getting the right the most optimal solution is there because somehow the way that Dijkstra do the relaxation, it is not going to revisit. It is basically if like let's say the negative edge is not being considered first, you're probably not going to be going through that negative edge. If you notice some of the edges here, when we look at this question, some of the edges we don't really consider. Okay, we don't go through that edge because maybe the notes has been processed, so we're not going to revisit it back. Okay, so that's why if you have a negative edges, there's a possibility that you're not going to get the most shortest distance because if you don't go through the negative edge first, then maybe you will not get the shortest path. Okay, so that's why we use the Bellman-Ford. Okay, so if like let's say you have a negative edge, you want to make sure that you get the shortest path, okay, between a single source to the rest, between one node to the rest of the nodes in the graph. We apply the Bellman-Ford algorithm. Okay. So here, if we look at the definition, same Bellman-Ford solve single source shortest path problem. Okay, and for in this case, the edge width the edge width may be negative. Okay. So basically in the algorithm, you will have some kind of Boolean value that indicate whether or not there's a negative rate cycle. Okay. So one of the even though that how do you call that? Even though Belmont can consider negative edge, but you can actually do some kind of test, okay, after you finish running the Belmont, whereby you can actually check for the negative weight cycle. Because if you have a negative weight cycle in your graph, then in that case, you are not going to find any ultimate solution. Okay, so basically, the algorithm will have no solution. Okay, uh, if there's no such cycle, you will be getting what are the shortest path from one node to the rest. Okay, so what is a negative cycle? It's like if, like, let's say for example, you have this graph. Okay, so maybe I will just draw like this graph. Okay, and then the distance, let's say if I put 3, this one 4, and then I put this edge negative 10. Let's see, for example. So basically, you can see that the total cost, if like, let's say, for example, this one 4 plus 3 is 7 minus 10, you're going to get minus 3, right? So this indicate this is actually a negative cycle. What do you mean by negative cycle? So if you have a negative cycle inside your graph, and if you run the Bellman-Ford, you're not going to get the solution. You will get partially because the but still you're not going to get the most optimal solution because of this negative cycle. Okay. So let's look at so basically this is the drawback of it. So we're going to look at how Bellman-Ford actually works. Okay. Uh, okay. So the Bellman-Ford, it is just like you still do the relaxation. Unlike the Dijkstra, we do not consider if, like, let's say the node has been processed, we don't consider, right? So we just consider what are the nodes that have not been processed. Unlike Bellman, it sort of like have an iteration. If, like, let's say for example, in this case, the V, the number of V is 5. Therefore, we're going to run the relaxation for V minus 1 time, which is 4 times. Okay, so we're going to run the thing for 4 times. So in Bellman-Ford, the process is that first we are going to take note what are the all possible edges. Okay, so we're going to take down we will take note what are the possible edges. So in this case, the possible edges that we can have from S. So basically, we're going to consider S as our starting point. And of course, initially, since what we're gonna initialize the distance for the rest of the node as infinity. So, and then we're going to keep track of what are the possible edges that we have inside the graph. Okay, so in this case, we have we have S to T, right? And we also have S to, oh, why is it so big? So S to T and S to Y, right? So we have this edge. So I think just for the sake of making sure that we have all the edges in. So we have ST, SY. Next, we're going to have S, and then we're going to look at T. So T can go to Y, TY, and then T can go to X, right? So TX, and we also can have T going to Z. T going to Z. Any more edges? No. And then we're going to consider the from X. X. So X can go to T. right? X can go to T, X, T. Any more edges? No. Okay, so X is done. And then Y can go to X. We have YX edge, YX. And then we have Y to Z. Y to Z. And then we have Z, Z going to X. Z going to X. And Z going back to S. So Z going back to S. All right. So these are all the edges that we need to that we have inside our graph. Okay, and we know that we're going to be we're going to be running the relaxation for 4 times. So we're going to run it for 1, 2, 3, 4 times. Okay, so same like Dijkstra, what we're going to do is we're going to be do the edge relaxation. Okay, so for the first iteration, so we can update this one to 6, this one to 7, and then we are going to choose T. So T, we're going to choose HT, right? We're going to we cannot do that. We cannot like have because you're going to do the iteration. So we're going to choose T. So T can reach Y 6 plus 8, so it's much more longer. So T going to X 6 plus 5 infinity, so we can update this into 11. T can go to Z, so this is -4, right? So 6 minus 4, we're going to get instead of infinity, we can get 2, right? And oh, sorry. Oh, we cannot do that. Sorry. I'm so sorry. We are actually doing the Dijkstra, but the reason why we have this is we have to follow this list so that we don't miss any edge. Okay. I'm so sorry. Okay, so actually we do like Dijkstra, okay, but we follow this edge. Why you have the edge but you don't want to follow the list? You want to like what? Okay, so we just follow this list. So we're going to be looking at ST. All right, so ST, in this case, ST, we relax this into 6. And then we look at SY. So SY, we can relax this into 7. And then we look at TY. We look at TY. So 6 plus 8 is 14. So at the moment, Y is 7. So we're not going to update anything. So TX, so T6 plus 5 is 11. Now it's infinity. So we can update this into 11. We look at TZ. So now 6 plus minus 4 instead of infinity. Now we can say it's 2. XT. So X to T. So currently X to T is 6. So 11 minus 2 is 9. So 6 is still the shortest distance. Y to X. So YX. Currently X, this is 11. 7 minus 3 is 4. So we can update this 7 minus 3. This one becomes 4. Okay. YX, and then YZ, 7 plus 9 is 16. So at the moment is 2, so we're not going to change anything. And then ZX, Z to X, 2 plus 7 is 9, but this one is 4, so we're not going to do anything as well. And Z to S, so 0. So yeah, so we're going to be we're not going to do anything for that one as well. Okay, so iteration 1 is done. So we're going to do the same thing again for the second iteration. So again, we go through the list. ST is 6. SY 7 is the smallest. Okay, TY, so TY, so 6 plus 8 is 14, 7. T to X, current now is 6 plus 5 is 11. So here it is 4, we're not going to do anything. And then TZ, so we have 6 minus 4, 2, so we're not going to do anything. X to T, so 4, okay, so X to T, so we have 4 minus 2, here we have 6, so we can update this, it becomes 2, right? And then YX, so Y to X, so we have 7 minus 3, 4, all right, so this is done. YZ now 7, this one is still smallest, we're not going to update that. ZX, so Z 2 plus 7, 9, so this is why we're not going to do anything. This one also we're not going to do anything. That is for the second one. We're going to do the third one again, do the same thing again by going through the list. So as going to T, we know that we can actually reach T with distance 2, okay, but so therefore we're not going to update. SY, okay, we're not going to update that one as well. TY, so TY, so 2 plus 8 is 10. No, we're not going to update that. TX, 2 plus 5 is 7. We're not going to update that. TZ, so 2 minus 4. This one we can update now. It becomes minus 2. XT, X to T. So we have 4 minus 2 is 2. We're not going to update that. YX 7 minus 3 is 4. We're not going to update that as well. YZ 7. No, we're not going to update that as well. ZX minus 2 plus 7 is 5. We're not going to update that as well. And ZS, we're not going to update that as well. And we're going to run it for the last time. The same thing we have to go through. So 6 2 no, SY 7 no, TY 2 but no, TX, do we need to update TX now? TX 2 5 no, TZ, do we need to update TZ to minus 1 and no, we're not going to update that. XT, so X to T 4 minus 2, no, we're not going to update that. XYX 7 minus, no, we're not going to update that. YZ 7, no, and then ZX, no. Okay, and therefore these are the final distance from S to the rest of the node. Okay, are you alright, class? So 2, 4, negative 2, 7. Yep. Okay. Any question about this one? Any question about Bellman for algorithm?
So the 4 times iteration is required.
Yeah.
Or
For Bellman for. So in order for you to determine how many times that you need to run this through all the edges is V minus 1. The number of vertices minus 1. So 4 times. Okay. And then I mentioned about you know, like making sure that there is no negative edges. Okay, because sorry, negative cycle. because in this case, for this um, how do you call that? For this graph, we do not have a negative cycle. You can do a check, okay, by running the relaxation algorithm on all of the edges again. If like let's say for the you go this and then some you have some inside the graph. Okay, so you so in a sense you can afford to get the stuff the two ratio. Is that all right? How whether negative cycle. Okay. So basically, by end of Belmont or maybe you know like I don't know maybe after iteration two that uh, uh, no there's no notes that is updating okay the value, then you can actually stop. Okay, so comfort should not run let's say it shows that inside your graph there is that negative cycle. Okay, are you alright for Belmont Ford? Okay,
Okay.
so the running time complexity of course this one is it depends on the age. So I think the running time complexity for this one is not VE. So you have N V V times E, and then yeah. So actually it is actually VE. Okay, so this is VE plus this flat. Okay, is VE. The running time complexity is VO of V times H. Okay. Okay, so right. You want to take a break for a while before we go to the Floyd Washer? Yeah, 5 minute break.
Okay.
Yeah. Okay. All right. There should be. It looks like there's a typo inside the slide. With function. Okay, so let's continue. Let's continue to the last algorithm that we're going to be looking today, which is all pair shortest path. But before we go and look into this all pair shortest path, so if you notice that when we do the Bell, when we do this Bellman for algorithm just now, we don't really apply the greedy approach. If you notice, what we did was we kind of like keep track what are the possible solution that you can get for all possibilities of like by going through all the edges. Okay, so basically we kind of like look at all the possible answer and try to and basically the solution is based from the uh, uh, based from the table or based from the calculation or the computation that we have made. So for the Belmont-Ford, it's a little bit different than Dijkstra because Belmont-Ford uses the dynamic programming approach, okay, whereby it's do some kind of computational computation, okay, and then we make we find the solution based on that computation, okay, based from the process that we go through, which is we have so basically we kind of we what we do is we look at all the possible values and we find what is the shortest or the smallest value out of the possible solution that we can get. Okay, so for Belmont-Ford, it is actually using the dynamic programming approach. We're going to be looking at dynamic programming next week. Okay, so next we're going to be looking at all pair shortest path. So just now what we did was we find what we were looking at is that we are looking for single source the distance single source to the rest of the nodes that we have inside the graph. Okay, so what it means by all pair shortest path is that if, like, let's say a we have let's say we have node A, node B, node C, node D, and then let's say these are connected somehow. I don't know, maybe something like this. Okay. Oh, there's a cycle. Yeah, you can actually have a cycle, but yeah. So let's say, for example, we have this graph, all pair shortest path. Just now, what we did was we find from A to either B, C, or D, right? So for all pairs shortest path, we are looking for the distance not just from single source, but we also want to know how do we get from B to A, C, D, C to A, B, and D to A, B, and C. Okay, so we want to find what are the distance for all these pairs. So we want to know how do we get from each node to the rest of the node. Okay, just now it's just one single node to the rest of the node. For all pairs is all we want to know what are the distance from any of the nodes, okay, to any other nodes that is in the graph. um okay so so if like let's say we want to use the greedy approach, what we can do is that we can apply the Dijkstra for from the starting point A, from the starting point B, from the starting point C, for the starting point D, for example, right? You can actually solve this problem by applying the Dijkstra for each of the node, okay, and then you find what are the distance for like let's say for all the pairs. And the running time complexity, if you remember what is the running time complexity for the Dijkstra, the running time complexity is the big O of V squared. So if we apply the running time for if we apply the greedy approach to actually solve this problem, we need to do this for all. So we need to run this for all the vertices that we have inside the graph. So therefore, we have to times it with so we're gonna be having like V squared times the number of vertices. So therefore, the running time complexity for applying the Dijkstra for finding the all path shortest path would be order of V cube. Right? Are you following me so far? Right? So that is if we are doing if we are using the greedy approach, we still can get the solution, but the running time would be order of V cube, right? So here so for the all path shortest path, you can actually find the solution by applying the Floyd-Warshall algorithm. Okay, so the Floyd-Warshall algorithm uses the dynamic programming approach, okay, to solve to find what are the shortest distance for all paths for all paths shortest path problem. Okay, if let's say you have a directed graph G. Okay. All right. Okay. So this one, I'm just going to show you a few steps, and maybe you can continue and doing this, and maybe we can, you know, um, discuss it during tutorial. I have been doing the. I've been using this example for a few times, but this is actually from Common. Okay, this is this example is taken from Common. But if I'm not mistaken, there are some mistakes in uh, two of these graphs, the last few graphs, sorry, the last few metrics that is being generated. Okay, so but I'm not going to do it in the class because it will take so long to actually get to the end. I want you to continue like after the class, and then see if you can if you compare with the answer here with the example here, and take note of which of the value that is actually not corresponding to this answer. Okay, but basically I'm going to show you how are we going to do this, right? um okay. All right. So I think it's better for me to have this done in the next page. All right. So first of all, what we need to do is that we are going to create an adjacency matrix for this graph. All right. Do you remember what is adjacency matrix? So basically, there are two ways of how we can represent the graph. So either you can use the adjacency list, or the other one is the adjacency matrix. Okay. So in this case, we need to create D0 of the which is this is the adjacency matrix for this graph. Okay, so let's try and do D0. So D0 is equals to, so I think like for me, I like to have the numbers in. So 1 2 3 4 5 1 2, 3, 4, 5. Okay, and then we're gonna create the adjacency matrix. So 1 to 1. So basically for this one, we know that there are no cycle. Basically self going back to itself. So we can just straight away put this as 0, 3 to 3 is 0, 3 to 4 is 0, 4 to 4 is 0, and 5 to 5 as 0. Okay, so this part will always be 0. And then we're going to see, so from 1 we can go to 2, and we can go to 3, we can go to 5 with the value 1 to 2 is 3, 1 to 3 is 8, 1 to 5 is -4, right? So for those unreachable nodes from 1, we're going to put it as infinity. All right. So we're going to do this for all nodes. Okay. So we look at 2. 2 can go to 4, 4 and 5. So going to 4 as 1, going to 5 is 7. Unreachable node would be infinity, right? 3 to 3 can go to none. Oh, 3 can go to 2. So 3 can go to 2 for value of 4. Unreachable one, we put infinity. 4. 4 can go to 1 and 3 with value 2 and -5. So unreachable one, we're going to put infinity. So 5 can only go to 4 of which of the value 6, and the rest unreachable one is infinity. Right? Are you guys following adjacency matrix? So this is the adjacency matrix for this graph. Any question?
So would the next step follow follow along the path to make sure they're able to connect with the other nodes, or
Basically by applying this Floyd's Warshall algorithm, basically in the end, the last adjacency matrix that you're gonna get will show you what are the distance from all nodes to the rest of the nodes. Okay, but to get to that last one here, there are like, let's say for example, there are 5 vertices here. So basically you are going to do the matrix for each you're going to create this matrix for each of the nodes. Okay, we're going to go through each of the nodes. So therefore we're going to, until we arrive to the last one, and this last one is going to show you the distance to each from, like, let's say for example this one, let's say from 1, let's say for example this one would be so if I write 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, and basically if you want to know what is the distance from node 5 reaching to node 2, you know that the distance is 5. If let's say you want to go from node 2 to node 5, you know the distance is -1. Okay, let's basically the last matrix will show you what are the distance between all the pairs. Okay, but to get to this one, you need to go through each of the how to call that, each of the nodes. Okay, we are not really going to look at the graph once we were just going to be referring to the previous graph. Sorry, to the previous matrix. Okay, so since we have this D0, okay, which represent the adjacency matrix for this graph, so we're going to move on to the next, to the first iteration of finding the all best shortest path. Okay, so basically, the next one. So let's say we call it as D1. The reason why we have to have, like, let's say for example you have 5 vertices, you need to have 5 matrices. It's like meaning is that we are going to consider all the nodes being the intermediate node. Okay, so let's say for example, in order for you to get let's say for example we want to go from node 1 to node 2. Okay, we want to also consider not just this edge but also this one. Okay, so this matrix will allow you to somehow keep track of what are the possible distances. So basically, the possible way for you to go is by going through straight away directly from 1 to 2, or 1 going to 3 to 2, or 1 going through 4, 6, 3 to 2. So basically, by calculating, or by generating these matrices, it's like you are keeping track of all the possible distances that you can get from all possible nodes. Okay, so but we're not, so in order for you to do that, like manually looking at the graph is if, like, let's say your graph is like this, even graph as big as this, it is almost like very difficult for you to keep track, okay, of the value. So by applying the Floyd-Warshall algorithm, by generating all these, because this algorithm will be using all these matrices to actually find what are the shortest path for all the pairs, by actually uh, 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 looking at all the possible solution, all the possible, how do you call that, cost or the weight for uh, all the possible path. Okay, so yeah, so basically that is what we're going to do. So let's look at, let's try to generate the D1 matrix. Okay, so basically what we are doing here, excuse me, 1 second, let me, I need to open something out first. Okay, so basically what we're going to do, okay, so basically what we're going to do is that we are trying to find out what are the, let's say for example we have node 2, let's say for example we want to find node 2 going to node 4 by going through node 1. What are the possible costs, if existing, the distance from going to 4 from 2 going through this node. Okay, so this is basically what we are trying to do here. All right, so that's why same goes for if let's say 2 going to 5, we are considering what are the possible distance going to 1. So basically the first matrix is, this is what we're going to that we are considering. Okay, so what we're going to do is that, let me draw back this one in case like one. I really hate doing this because I always get mixed up. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. All right. And then for D1, we are not going to change anything that is under 1. So basically we can just copy back this value in to D1 as well as this one. Okay, so we're just going to straight away write back the value. So this one is 0, 3, 8, infinity, -4, 0, infinity, infinity, 2, infinity, 0, 0, 0, and 0. Okay, and now we're going to fill up the rest of the value that the rest of the value. Okay, so in this case, the first value that we're going to find is that what is the distance for this edge? 2 to going to 3. Okay, by going through node 1. So therefore, how are we going to calculate this? Is that we're going to be referring to D0. So what we're going to do is we're going to find what is 2 to 1, which is going to node 2 going to 1, and 1 going to 3. Okay, so 2 to 1 and 1 to 3. So we're going to find out what is the value for this based from the previous matrix that we have generated. So what is 2, 3? What is the value for 2, 3? It would be infinity, right? This one, 2, 3 is infinity. 2, 1 is infinity. 1, 3 is 8. Okay, so if we see here, this one is actually smaller than this one. If we add infinity plus 8, this one is actually bigger than infinity. So therefore, we are going to say that 2, 3 would be infinity. And then we go and do it for the next one, which is 2 to 4. So we have 2, 1 and 1 to 4. So what is the value for 2, 4? 2, 4 is 1. 2, 1 is infinity. And 1, 1, 4 is infinity. Right? So therefore, therefore 1 is actually smaller than infinity. Then this value should be 1. Are you following so far, class? Do you know what I'm doing right now? So the next one we're going to find out is this one, this value here, which is 2, 5. So we're going to find what is the value from 2 to 1 and 1 to 5. By looking at the previous one, we're going to get 2, 5. What is 2, 5? 2, 5 is 7. And then 2, 1 is infinity. 1, 5 is -4. So we're still going to get this one smaller. Therefore, we're going to keep the smaller value. We're going to find the minimum between either this one or the one that will go through the intermediate nodes. Okay. So in this case, 7 is smaller. So we're going to keep 7. So next one, we're going to find out what is the value here for 3, 2. Same thing again. So 3, 2, 3 going to 1 and 1 going to 2. Looking at the previous matrix, 3, 2 is 4. 3, 1 is infinity. 1, 2 is 3. Okay, so if we add this, 4 is still the minimum. So therefore, we get 4 here. Are you following so far what I'm trying to do here, class?
So we're basically just going at this step we're going through like between the chosen node. For example, right, at the moment we're choosing like 2 to want to go to node 4. We're going to decide between taking 2, 4 or going to 2, 1 and then 1, 4.
Yes. either directly or going through node 1.
Does it make a difference if we decide like if we decide to go from the bottom instead like 2554 or?
Yes, of course, because okay, so the reason why we do this is right now we are only considering that it is going to go through node 1. So remember the distance that we update that we find out that we update would be the shortest distance through to go to that one from the previous node somehow. So the concept here, so for the first matrix, we are considering going through node 1. Okay, so I'm going to, so basically the step in order for you to fill up this matrix is basically the same step. Okay, it's going through node number 1. So once finished, you're gonna get this graph, this matrix. Sorry, you're gonna get this matrix. All right. So let's just fill up. I'm just gonna follow this one. Okay. So infinity, 2, 5, -5, 0, -2, infinity, 6 and 0. Okay, so basically this would be your D1 going through node 1. So for the next step, we are going to create matrix called D2, whereby we are going to consider any nodes going to node 2. Okay, so let's say for example, let me draw this one again. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, and now we are going to refer to the previous one. So since we are doing D2, we're going to refer to this matrix D1. And in this time, since we are considering going through node 2, we are not going to change anything, any value from this node. 2 and this. So the value is going to be the same as well as this 0. Okay, so we're just going to be copying in to this how do you call that, this new matrix. So 0 0. So I think I better copy it in the this one first. So 3, 0, 4, 5, infinity, and 2, it will be infinity, 1, 7, 0, 0, 0, 0. Okay, same thing. We're going to fill up those missing ones. Okay, this time it is supposed to go through node 2. Okay, so in this case, what we're going to do is that this value is missing, so we are going to find out what is the value from 1 to 3. Either we have the direct one is much more smaller, or going through 2. Okay, so 1, 2, or 2, 3. Okay, so we're going to refer to the previous one. So 1, 3, in this case, 1, 3 is 8. Okay, 1, 3 is 8. 1, 2 is 3. 2, 3 is infinity. Okay, so 3 plus infinity is bigger, so therefore we're going to keep the value 8 here. All right, and then the next one would be finding 1, 4. So we're going to see 1 going to 2 and 2 going to 4. So 1, 4, what is the value for 1, 4 is infinity. 1, 2 is 3. 2, 4 is 1. Okay, so 3 plus 1 is 4. So 4 is smaller than infinity. So we're going to put the smaller one here, 4. Are you good? Are you following so far? So the last one is we're going to find what is 1, 5. So 1 going to 2 and 2 go to 5. Okay, So 1, 5 is -4. 1, 2, 1, 2 is 3. 2, 5 is 7. So 3 plus 7 is 10. -4 is smaller. So therefore, this value would be -4. Okay. So you fill up the same way. We find what is 3, 1 going to 3, 2, 2, 2, 1. Okay. And then we fill up the matrix. You are going to get this matrix. Okay. For D2. So we fill up. So again, I'm just going to skip and just copy this one in. So 3, this one will be infinity, 4, 0, 5, 11, 2, 5, -5, -2, infinity, 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 6, 0. Okay, so this would be your D2. So again, we do it again for D3, and this time we assume that this is going to go through 3. Okay, same thing. So for this one, we are not going to change this value. Oh, sorry. We are not going to change this value and this value. This value, of course. Okay, so let's so basically for the rest of the number, we have to find what are the value using the same method as well, but this time it is going to the node number 3. Are you following so far? Do you see the steps? Right?
Yes, yes, yes.
Right? So basically for this one, this will be just the same matrix. So this one, we say that we don't change this one. These are not the one that we are basically that one would be not unchanged, not changed. And then for D2, we're going to take the second one. Okay, so if you notice this row and this column does not change in D2. And then for D3, we are going to keep this value, okay, in. So if you see that this value inside D3 is the same, so D4, we're going to keep this value in. So here, you will see that this value is the same as this value and this value, right? And the last one would be, you are going to copy it back in this value into this, and then you're gonna be solving the rest using the same method as well. Okay, so for this for D4, you have to go to node 4. For D5, you have to go to node 5. Okay, and so on and so forth. And finally, you're gonna get the final answer, and that final answer is going to be showing you what are the distance from all pairs to the rest of the nodes. Okay. And yeah, I don't think we can calculate this until right now. So for those for you to practice, maybe you can try to complete this. I had the feeling that there's an error in this example because I never get to finish until 4 and 5. But you can try, and then if there is a mistake, then we can discuss in the class. Okay. Sorry, in the tutorial. Okay, so for the Floyd's algorithm, as I mentioned, since if you know, since basically the approach, as you can see, it is actually calculating, like keeping track what are the possible solution for all combination of path. Okay, so in this case, it is using the dynamic programming approach, and basically the solution is while you know all the possible answer to all possible combination, we can actually get the most optimal solution for all pair shortest path using this Floyd algorithm. Okay. Okay. Any question about today's lecture?
So the time complexity is what?
Oh,
Cube.
okay. So for the running time complexity for this one, It would be up until n, yep. It would be n cube as well.
Okay.
Right. So if you see here, so this one, the runtime complexity would be this one would be n. Okay, and then this one is also 1 until n, and then we also have this nested loop n. So n times n times n, we're going to be getting order of n cube, right? Okay. Any question, class? Okay, so if you look at the pseudocode here, we are looking for the minimum, and basically between the one with uh, what what we were doing just now. I already closed that window. So we basically we try to find what is this the smallest between the two possible answer. Okay, and then we're going to fill up the matrices. Okay. So if we have no more question, I guess I will see you during tutorial. Try to see whether you can get till the end, because I had the feeling that one of the metrics in this example, the answer sort of like got jumbled up. It's either my previous students also like me, like after a while you get overwhelmed because like there's so many calculation that you need to do, that we never get the exact answer like the example, or it is actually there's an error inside this example. Okay, so I don't know whether this batch can actually uh, get into to the end and just prove whether this example actually has an error or not. Okay. Okay. Do you have if we have no more questions, so I guess I'll end the class for today. Yeah, so I guess I will see you during tutorial. Okay.
Sorry, doctor. I have a question.
Yes.
So for this algorithm, do you, as you mentioned that it consider all the combinations, right? But let's say the path from 1 to 3, we take 1, 5, 4, 3. So, but when you doing the matrix of D5, you only consider 1 to 5 to 3. I mean,
If you notice, what we do is that we sort of like gradually calculate the possible value, because we are not referring to D0. We are actually referring to the previous one, which is already calculating all the possible path going through the whatever available combination before. Did you notice?
oh, okay. I think I would try it first.
Yeah. So basically, this algorithm will be considering all the possible one, because if you notice, it gradually try to find what are the possible, like let's say for example, D0, like for example, 1 going to 3 through 2. Okay, in 1, 2 going to 4 through 2, and so through 3. So basically, you gradually build that, and you are actually finding what are the possible shortest path at that point, gradually. Okay, so in a sense, by applying this algorithm, you are actually calculating, just now as I mentioned, if you look at this graph again just now, if you want to get to 1 to 2, you can either go straight from 1 to 2, or 1 3 2 going to 3, 1 5 4 3 2. Remember, of course, to get to 2, let's say for example the shortest path is going to 3, and basically before we get to 3, we already calculate what is the shortest path from 1 to 3, from 4, 1 to 4 from 5, and so on and so forth, from the previous matrices. Did you notice that is what we do? So
yeah.
basically, up until the end, we are actually we basically we sort of like already consider what are the previous
Okay.
um
Understood. Thank you, doctor.
okay. All right. So I guess I'll end the class for today. I'll see you during tutorial. All right.
Thank you,
Okay.
Doctor.
Thank you everyone. Assalamualaikum warahmatullahi wabarakatuh.
Salam.
Bye.